All right, welcome everyone to today's CDAC webinar. I hope everyone's doing well. For this, our final webinar of 2023, we're delighted to feature Malcolm McMahon from the University of Edinburgh in the UK. Malcolm is one of the eminent scientists broadly in the field of matter and extreme pressures, and he should not be confused with another Brit, Malcolm McMahon, the 9th Archbishop of Liverpool. Our Malcolm is a leading high-pressure crystallographer, having literally written the book on the really quite astonishing and intricate structures that even simple materials take on at high compression and how to unveil those properties using X-ray diffraction techniques. And that was the subject of his 2006 Doctor of Science thesis, which I highly recommend to everyone. Since then, Malcolm has moved into dynamic compression and combined static and dynamic compression, pioneering new diffraction techniques, among others, at X-ray light sources and uncovering numerous phenomena along the way, which I hope we'll hear about today. Malcolm obtained all of his degrees from his bachelor's through his PhD and his Doctor of Science from the University of Edinburgh, and his work has led to numerous awards, including fellowship in the APS, the Royal Society of Edinburgh, the Humboldt Research Award, just to name a few. Malcolm is also an entertaining and sought after dinner speaker. And since this is after dinner in Edinburgh, Malcolm, we're looking forward to your after dinner speech.
Excellent. Thank you very much, Russ, for those kind words of introduction. Yes, it's just after 7 o'clock in the evening here. I thought of bringing up a glass of whiskey with me, but decided that would be slightly unprofessional. So yes, recent advances in static compression science at synchrotrons and XFELs. Which one is? Oh, come on. Oh, here we go. Okay, so as Russ said, my training way back was in crystallography. And I was lucky in a way that as I finished my PhD in 1990, that technique advances in Japan meant that we could do much better crystallography at synchrotrons of samples in diamond anvil cells than we'd ever been able to do before. And so by 2000, by the change of the millennium, it was clear that almost everything from a crystallographic point of view, a structural point of view, was more interesting at high pressure than it was at ambient pressure. And a simple way to demonstrate this is if I take the phase diagram of lithium as published in David Young's book in 1990, and compare it to the phase diagram of lithium from 20 years.
Which would stand in stark contrast to the old way of calibrating NBI, which was the LCAL system. This was a laser that...
Okay, 2 seminars for the price of one. The phase diagram of lithium from 20 odd years later, and you can see the pressure has gone up by a factor of 12, high and low temperatures, exotic melting curve, and a multitude of low symmetry complex phases with as many as 88 atoms per unit cell. And I think if I was trying to highlight this science to anybody, I would use the example of sodium, which goes from the kind of nearly free electron, kind of perfect simple metal at ambient conditions, to a transparent insulator above about 190 GPa. And there's 2 pictures from Edinburgh samples seen in transmitted light. It really is a remarkable sample that it goes from the shiny metal through a black semiconducting phase, to this transparent phase at 200 GPa or so. Our son is doing the periodic table in his science classes at school at the moment, so we bought this jigsaw for him, and I said, isn't it cool that your dad has published all these papers on all of these elements? And he quite clearly couldn't care less. But over the last 20 years in Edinburgh, we have probed a number of elements of the periodic table. Some of the other ones we haven't looked at because many other people are looking at them, hydrogen, iron, etc. And quite a few in the middle there aren't particularly interesting from a crystallographic point of view. But we've got our eye on 3 more for the coming year once we get back to the synchrotrons. So what I'm going to focus on for the first half of this today is on the structural systematics of the lanthanide elements. Now, I have a big folder of papers somewhere in a box underneath my desk from papers I photocopied in the 1990s and read about how these elements, as we're filling the 4F shell, undergo a very, very similar sequence of phase transitions, but with the phase transitions shifted slightly in pressure. So with the exceptions of europium and ytterbium, which are much more like the alkaline metals such as barium, you can see just from the colors there, the systematics of the structures they adopt as we move from the lower Z members on the left lanthanum to the higher Z members on the right. And we go from a series of structures where it's just stackings of HCP layers, HCP, double HCP, FCC, samarium type, etc. And then at higher pressures, it gets much more complicated, and we get these so-called collapsed phases where there are first-order phase transitions, and we see more complex phases, including the alpha uranium structure, also seen in the actinides, for instance. And what I'm going to focus on today is this MC4 structure, this monoclinic structure here, which there was a lot of work in the first decade or so of the millennium with, as people pushed up to a couple of hundred GPa, looking at this structure in all of these elements. Now, I can't remember why we started to look at this. I think it was because terbium, up at the left here, goes into this phase at the lowest pressure, and we wanted to see what would happen next. So we loaded up a sample at the SRF synchrotron in Grenoble, in helium, got extremely high quality diffraction patterns, and we hit a problem in that while the MC4 structure fits quite well to the observed peaks at low angles, there's this peak here which it just cannot fit. There is no way the MC4 structure can account for that peak. And if you look at all the diffraction patterns published on these MC4 phases, that peak is there in all of those patterns as well. And you can see all over here, there's no tick mark underneath it. So it was clear at this point that the MC4 structure was not the structure of the lanthanide elements at these pressures. And I think this project then outlasted 2 PhD students who tried and just couldn't quite understand the data. And maybe one of the advantages of having a kind of tenured position is you can just keep plugging away at these things on every Friday afternoon. And it was one Friday afternoon where I tried something different and got a structure that fitted perfectly. So this is an orthorhombic F-face-centered structure, 16 atoms, with this very, very high symmetry. And once we knew that, we could look at the supposed MC4 structure in neodymium and samarium, and it didn't fit. It was not the same structure. It was another FDDD, exactly the same space group, but with only 8 atoms in the unit cell. And this is a known structure of plutonium, one of the ambient pressure, high temperature phases. I think it's gamma plutonium. So again, we see this link between the structures in the actinides, gamma plutonium, and this structures we were now seeing in the much easier to work with lanthanides. So they have exactly the same space group. One has twice as many layers as the other. And these are, again, structures comprising close-packed or quasi-close-packed, quasi-hexagonal layers. But instead of each atom in each layer being above the midpoint of 3 atoms in the layer below and above, these layers slide to sit at the midpoint between 2 atoms in the layer above and the layer below. So they're tenfold coordinated, 6 in each layer, 2 above and 2 below. And then their only difference is the stacking of the layers. And unlike when we stack above the midpoint of 3, there are now 4 ways of doing this, A, B, C, D. And that's the only difference in these structures, is the stacking of the layers. But if you go back and look at the initially reported monoclinic lattices, you can see there's a very clear relationship between the two. So there's the OF8 and the OF16 lattices superimposed on the lattices from the previously published MC4. So it's not surprising MC4 gives a good fit, but the slight differences in symmetry means it can't explain that kind of extra rogue peak. So that's now what the systematics of the lanthanides looks like. This HP3 structure here, here, and here is another one. It's the same member of the same stacking sequence where each atom sits above two of the others. So it's beginning to look quite good in terms of the systematics, but we have a slight problem with this guy, that this isn't the same as this. This OP4 structure in praseodymium's only been reported once before and has only been seen in praseodymium. So we went and had another look at this. We got good quality diffraction patterns up to 200 GPa. And here are all the calculated peak positions here underneath the pattern. And you see the pattern is a lot simpler than the number of calculated peak positions would suggest. The key 102 reflection, which was seen in the previous study and should be there, we don't see. But if we compare this pattern to the Ti2 phase of cerium, seen way back in the 80s, then it bears a striking resemblance. And sure enough, you can fit this phase of praseodymium with that Ti2 structure, therefore bringing it back into the same structural systematics of the other elements. And we get beautiful equations of state of these materials. And one of the reasons for this is that the Petra 3 synchrotron in Hamburg now has a sub-micron beam. It's about 850 nanometers by 850 nanometers. And we've become big fans of using this because it really does give excellent quality diffraction data. And also, if you have a diffraction pattern with both your calibrant and your sample in the same 1 by 1 micron spot, then there is a great deal less uncertainty about the pressure at which the sample you're X-raying is at. So let's just have a brief description of the P02.2 beamline at Petra, run by Peter Lehrman, Hans-Peter Lehrman. So as I say, they've got this beam, 850 microns. That was earlier this year. As of a few weeks ago, Peter tells me that it's now down to 0.6 by 0.6 microns. And they're using compound refractive lenses, beryllium, I would guess, to do this focusing over long distances. And then if you read in this paper, 2022 paper, they've got this final correcting faceplate to reduce the tails on the beam and improve its shape. And as I say, we've become big fans of this beam, and it allows us to do, as the beamline control software also on the beamline makes doing grid scans ridiculously easy. The thing that takes the longest time is changing the name of the files when you do the next grid scan. But here is a 10 by 10 micron grid scan showing the pressure and GPa across the sample. And you can see, even though the pressure ranges from 185 to 193 GPa, if our sample and our calibrant are both in that spot there, then they are both at 193 GPa. And we get extremely high quality diffraction data. Very little sign of any broadening from pressure gradients, for example. Excellent Rietveld fits. And we now grid scan everything. So here is a sample of iridium. The iridium is up here in bismuth at 148 GPa. We've become big fans of doing grid scans to determine the uniaxial pressure, how non-hydrostatic is the pressure. And we now collect hundreds of spectra and then analyze them using Singh's peak displacement method to determine the non-hydrostaticity. And again, here from a recent study of a sample at terbium at 270 GPa, the black line shows the QLit, the dashed line is the sample, and again, the black dot is the size of the full width half maximum of the beam relative to the gasket hole on these, 30 micron QLits. And so this meant we were looking for a better PTM for multi-megabar work than helium. Why were we trying to do that? Because we had problems with the gasket hole initially collapsing when we loaded helium or neon as a high pressure gas at a kilobar or so, and then trying to take that sample up to 300 GPa. And then Singh had published, what, best part of 20 years ago now, that bismuth could be a good PTM. It's not transparent, for instance, so you're not going to do any laser heating with a bismuth PTM. But in terms of a material which remains soft and generates hydrostatic conditions up to multi-megabar pressures, then bismuth is excellent. So again, here are grid scans of our gasket hole of our copper in bismuth. Again, all collected with grid scans. The downside of all of this is we collect huge amounts of data these days. But here are our own measurements of the uniaxial strain component in the bismuth up to 300 GPa, and you can see it's generally below 1 GPa. The interesting point is just before this sample failed, and this sample failed, T, this uniaxial component, turns negative, which suggests that the pressure out the way is higher than along the axis of the radial stress is higher than the axial stress just before diamond failure with both of those samples. But bismuth is an excellent PTM. It has disadvantages, but in terms of generating a hydrostatic environment up to multi-megabar pressures on strongly scattering materials, it's very, very good indeed. And here, for example, in that sample here, there is the uniaxial pressure, a T-map over the gasket hole, 2 micron steps, 2 seconds a point. And I just point out the previous study used a beam that's bigger than that entire square. It was 26 to 30 microns across, and they were collecting a single 15-minute exposure. We're now collecting hundreds of exposures of 2 seconds each, and it all has to be analyzed, of course. And again, just emphasize the point, excellent quality diffraction data up to multi-megabar pressures. So that leads me on to the other big synchrotron in Europe, the ESRF. And the ESRF, like the APS at Argonne and Spring 8 in Japan, is completely changing the magnetic lattice in the ring. The ESRF has done this and is back up again. I believe the APS is down at the moment to do this. And the main thing that happens is that the electron beam is going to shrink, or has shrunk, by a factor of about 10 in the horizontal direction. And so, for example, this is a pink beam of what's that, delta E over E of 0.5%, straight from the undulator. You get rid of this horrible asymmetry here that, if you look at the work Livermore has been doing on DCS at the APS, this gives these asymmetric peak shapes here. But once the APS comes back up again, these things are going to sharpen up and become much more Gaussian-like than this. So we've got 1,000 times more flux at the new machine to study, highly dilute, low Z materials. This greatly reduced horizontal emittance means that the X-rays are much easier to focus. So again, at the SRF, we can get sub-1 micron beams. It's got much higher coherence, better imaging. And the ESRF has also splashed the cash on better detectors, cadmium telluride detectors. And the great thing about these is that they have very fast readout, very high X-ray absorption, very little distortion of the images. So what you get are these very high resolution, high quality profiles. We can collect a second in image, and here, for example, is a beautiful diffraction pattern of a hard metal like rhodium in bismuth at 190 GPa, and you can see the Labai fit along the bottom is beautiful. And again, lots of maps of things. Here's the culet, there's the gasket hole on the culet. We can then focus in on this T-map, and this is done in what, 5 micron, maybe 4 micron steps, and we can then go in and look at one of these in a much higher resolution as well, using micron steps at the second point to look at variations in pressure, uniaxial strain component, etc., etc. The downside is we're collecting thousands of images. In fact, we discovered recently that rather than trying to find the calibrant within the gasket hole, for example, it was much faster just to collect a 10 by 10 grid, find the one pattern out of the 100 that had the calibrant in it, and throw away the other 99. And so in a 4-day experiment on Mohammed Mezwar's beam earlier this year, we collected over 600 gigabytes of data in 4 days. And again, there's iridium in a bismuth PTM, again showing, I think the bismuth T is the solid points, and the T in the iridium, the very hard iridium, are the unfilled points there. Okay, so getting this beautiful data has also awakened interest in fitting equations of state to our data. Now, in the past, it surprises me that we didn't do this. And if we did do it, we typically just did it in order to put a dashed line through our data points, maybe compare our K and K prime as determined by the equation of state with previous experiments or with theory. I think the people doing planetary and deep Earth modeling have taken this much more seriously, because knowing the bulk modulus or of a material at deep Earth conditions is important for modeling. And also for the exoplanet people, you're going to want to extrapolate equations of state determined up to 1 or 2 megabars to maybe 1 or 2 terapascals to predict the behavior of materials deep in exoplanets. And people have typically used the Birch-Moynihan EOS, which comes from elasticity, first order elasticity theory, or the Vinay EOS, which comes from DFT calculations done by Rose. Both of these equations of state, they work well, particularly the Vinay EOS works well, but they do have this problem, and I think this was Ron Cohen rather than Marvin Cohen. This is Ron Cohen's article. But one failure of the Vinay equation of state is that at very, very high pressures, extreme compressions, it doesn't merge into Thomas Fermi behavior. Things begin to diverge, which is non-ideal. And this is something that Wilfried Holtzapfel looked at in the 90s and the early 2000s. He wrote a good half dozen very, very good papers on a multitude of different equations of state. And at the end of all that, his preferred equation of state was this adapted polynomial of order L, the APL equation of state, which does merge into Thomas Fermi behavior at extreme compressions. And this expression here is integratable in order to get out free energy and things like that. So you can work with this equation of state through thermodynamic relationships to get out a large number of thermodynamic parameters. And the second order form of this equation, the AP2 form, is the typical expression people would use for fitting normal materials. And what you can do with this, as you can do with other equations of state, is linearize it so that your PV curve now becomes ideally a straight line, and it looks like this. And if we take, for example, the excellent data that Agnes Deval published in this 2004 paper, this is our go-to paper whenever we're doing anything on equations of state, because she gave all the numbers, and you can do whatever you like with them. That here in this APL equation of state, once you linearize it, you should get a straight line, and that straight line should, for simple materials, extrapolate to the origin. Now, this is logarithmic in pressure. This is gigabars probably up here, black hole type stuff up here. But you can see that this should be up a bit. This should be platinum, copper, and aluminum, all extrapolate to the origin. So simple behavior of materials under compression would be linear in this AP2 linearization and should extrapolate to 0. And you can actually fit these in the extreme case of just an AP1 equation of state, where there's only a single refinable parameter and K prime comes from the K naught. So to quote Holtz-Apfel's own words here, what you can do is use this behavior in linearized space to determine whether you have a simple material, a regular material, or whether the compression is anomalous. So here are materials exhibiting simple behavior, so lead, group 4, elements here, so straight lines, all extrapolating towards the origin. Then we have regular behavior, which give us straight lines, but not necessarily extrapolating to the origin. And then you have anomalous or irregular behavior, where things are non-linear, and as a result of phase transitions and changes in electronic structure, then you get distinct changes in gradient, most obviously here in bismuth. So once you go into this bismuth 4 phase and bismuth 5, then you get this something which looks much more like the regular compression of regular metals, straight line extrapolating towards the origin. Okay, so some examples from our lanthanide work. So here's samarium. If I fit just up to, what, about 40 GPa or so with a Vinny equation of state, something like that, you can see above 40 GPa, all of a sudden samarium stiffens up and is a lot less compressible than you would expect if you just extrapolated from the fit to lower pressures. And we can see that in the linearized plot, that this positive gradient here suggests the material is more compressible than you would expect for a material with that number of electrons having that atomic volume. But once we get into the HP3 phase, and particularly in the OF8 phase, we get this strong linear behavior pointing up towards the origin somewhere. So irregular compressibility through the phase transitions, and once it gets to OF8, the compression is much more that of a regular metal. You can see the gradient here is pretty parallel to that in gold and platinum from Agnes's data. So here's yttrium, and again, similar behavior, positive gradient. Once we get into the OF16 phase at, what, about 100 GPa, we get this change in gradient, and now we get this linear behavior here, again, pointing up towards the origin. And the best examples of all, so we've looked at potassium and rubidium up to 250 to 300 GPa, and there's the compressibility of rubidium up to 250 odd GPa, where V over V naught is 0.11. So this is 9-fold volume compression by the time we get up to 260 GPa. And if I compare the compressibility of rubidium with the compressibility of yttrium, which is, just 2 elements to the right, then you can see, they agree pretty well here, but then we get this marked change in behavior here, 25 GPa, and below that pressure, the rubidium is much, much more compressible than yttrium. And if we look at this in the linearized plot, it's great that we have so many data points here that we get rubidium does this. Then, remarkably, rubidium 2 and rubidium 3 are more compressible than the ambient phase. So it compresses, then it becomes more compressible in rubidium 2 and rubidium 3. And then once we get through this final transition, it now straightens up and again gives us the gradient we would expect for a regular metal. And this change that rubidium 2 is more compressible than rubidium 1, you can actually see if I blew this up, but we hadn't seen it before, nobody had commented on it before, but once you've got this unusual S-shaped linearization, the change in compressibility here is quite marked. Once you know it's there, it's obvious. Okay, so that's what we've been doing on the synchrotrons recently. So given that we have submicron beams and high energy beams and wonderful detectors and Damble cells that will go up to hundreds of GPa these days, what new things can we do at X-Cells that we can't do at synchrotrons? And in particular, being in Europe, I'm thinking of the HED beamline, on the European exfil in Hamburg. Well, we began thinking about this a long time ago now. So this was the first DAC workshop held at DAISY. The number of faces there you will recognize. And as a result of that workshop, there was a conceptual design report prepared for European exfil on how we would do diamond anvil cell studies on an exfil, the European exfil, with this purpose-built interaction chamber, which it shares with the dipole laser compression setup, but built to do DAC work. And I think the key point that distinguishes DAC work at an exfil from everybody else's work is that the exfil pulses will vaporize anything they hit. And that can't happen in a diamond anvil cell because your sample is clamped at tens, hundreds of GPa. It's got nowhere to go. And so that, I think, is what distinguishes our, the community's exfil science from everybody else's. That we want to get many, many shots from the same sample rather than blowing a hole through our sample or vaporizing it and then just moving another sample into its place. That doesn't mean we don't blow holes through them in the DAC, but it would be nice to get some science from them before we did that. So here's the setup. That's IC2. I think this is the temperature measuring system here. And inside we have a carousel for loading in, I think it's 5 or 6 diamond anvil cells. Here are the 2 big Varex detectors where the straight through beam goes in between them, like that. You can't align your samples as we would on the synchrotron by scanning them across the beam, because the beam would literally cut your sample in half or cut the gasket in half. So there's a lot of optical alignment goes on, and you're always worrying about the exact location of the samples along the beam and stuff, but we've worked that out over the last few years. So, and then it's very much like the synchrotron. We collect these 2 diffraction patterns on the top and bottom detectors, integrate them up in dioptas, and you get out beautiful diffraction patterns, which have a much lower background down here because there's no air scatter, because the tank is evacuated. So I'll just describe some results from the first DAC experiments that got done on European exfil. The first one was 4 years ago now, when we hadn't heard of COVID, which was led by my colleague Stuart McWilliams. I led one 2 years later when we had heard of COVID, and there were 2 more experiments done in that second phase as well. So before we did this first experiment, it wasn't clear if we put in a single full power pulse from an exfil, whether we would just hear a click as the diamonds were vaporized, in which case DAC science was going to be limited at exfils. So it turns out, yes, they do survive. In fact, they're remarkably difficult to break, even at megabar pressures. Can we use exfil pulses, the X-rays themselves, to heat the samples? Yes, we can. It's remarkably easy, in fact. Can we heat LOSI samples indirectly using couplers? Yes, we can. Can we couple a train of exfil pulses, 10, 20, 100 pulses, with a single pulse of infrared laser heating? Yes, we can do that as well. And can we couple a longer train of exfil pulses with a dynamically driven DAC and therefore collect diffraction patterns at different pressures from a train of pulses? And yes, we can do that as well. So it is very easy, very, very simple models of, well, there's about a millijoule in a pulse and 10% of it gets absorbed by the sample, and it's in this many cubic microns, and the heat capacity is this. You can heat your sample up to tens of thousands of Kelvin. It's unavoidable, in fact, and this is why people do plasmas and things like that at exfils. It's very easy to heat your sample up. One problem is there's no split and delay facility on the HED beam line at the moment. And all you can do is bring in your X-ray pulses 222, 444, or 888 nanoseconds apart. In the future, it would be nice to bring in one pulse and then bring in another pulse a nanosecond later. Use the first pulse to pump it and the second to probe it. But at the moment, we're stuck at 222, 444, or 888 nanoseconds apart. So what happens when you bring in a pulse? Well, the first thing you've got to do is keep your sample separated by a medium from your two anvils. Otherwise, it's not going to get hot at all. So we know how to do this from years, decades of laser heating experiments. The pulse comes in. There's lots of interesting physics happens as to how your material heats up. It will heat up. That heat then flows over the next microsecond or so. And 222 nanoseconds after the first pulse comes in, a second one comes in, probes the state of the sample at that time, and heats it up again. So if you were to monitor the temperature of your sample as a function of time, it's a sawtooth. First pulse comes in and heats, second pulse comes in, probes the state created by the first pulse and heats it up again, third pulse probes after the second pulse and heats up again. And you can vary how much energy you bring in with each pulse as to how quickly you want this temperature rise to happen. And I say, the beam will blow holes through everything. So this, from our first experiment, was a test sample of a piece of tantalum. So these are single and multiple pulses of hitting the tantalum. Now, if you look at these things, they're beautiful. So that was a single 25% full power pulse hitting the piece of tantalum. And you can see it's vaporized it. And we have all of these melt features around here. That's a full power pulse. They're a much bigger hole, and it looks like Mr. Whippy ice cream around the outside here, even though the melting temperature of tantalum is well above 3000 Kelvin. And I had a postdoc who was supposed to be doing experiments at Exfil, but because of COVID, we did LAMP simulations as well, and he did a very interesting simulation of what's actually happening in this material. You suddenly heat it to, in 100 picoseconds, tens of picoseconds, it goes from room temperature to, let's say, 10,000 Kelvin. Because it's heated isochorically, the pressure is also very high. So you have very high pressure liquid tantalum, and over the next nanoseconds, this thing blows itself apart, and you're left with a hole and this Mr. Whippy ice cream effect from the molten tantalum. And this is what your clamping your sample in your DAC at a megabar prevents. All of the physics still happens. It still gets hot. It's isochorically at a very high pressure. It's just what happens after that is different when your sample can't blow out because of the pressure being exerted on it. Okay, so when we first did these experiments, we had only these Varex detectors, which could only collect, if we put in 10 pulses, the 10 diffraction patterns from those 10 pulses would all be superimposed on the detector. We couldn't refresh the detector after each pulse, and I've described what we'd get here. And to see what we see in that case, this was a nice example. So this was a piece of copper in a sodium chloride PTM to keep the copper off the diamonds. And this crystallite here was in a nice position that it gave a nice sharp spot. So the first pulse gave ambient pressure, ambient temperature, sodium chloride. The second pulse probes the hot state created by the first pulse, third pulse, fourth pulse, fifth pulse. Okay, so this was 6 pulses in total. We can just get the temperatures here from the thermal EOS of sodium chloride. So you can see the temperatures of the NaCl. Why don't we see the 6th pulse? Well, there's a chance it was a liquid. So remember, these are the temperatures after it's heated up and cooled down for, I think it was 440 nanoseconds in this case. So it could well be that this last pulse had heated it up above the melt, and because of latent heat effects, it still hadn't cooled back down below into the crystalline phase before the next pulse came in. So those first experiments have already begun to produce papers. So we were doing some synthesis. So we had iron, and these were huge collaborations. You can see the number of people who were taking part in these first experiments. This was just iron and nitrogen at 5 GPa, hit by various pulses, numbers of pulses at various energies. You know, you could actually physically see what the X-rays were doing to the sample. And you know, it created this iron nitride, and we still have papers ongoing. The X-ray heating is very complicated because you are heating and probing with a beam of the same size and shape, and that greatly complicates things compared to using, you know, ideally a flat-topped infrared laser to heat your sample and probing it with an X-ray beam that's a lot smaller than that. Pumping or heating and probing with a beam that's exactly the same size complicates things. The paper on street optical pyrometry came out recently, and we collected a lot of data on high pressure temperature iron, looking for the high temperature phases, which we could see. This was a nice example. This was done by many of the same team, but this was done at the PAL exfil in Korea. So this was an attempt early on to see, could we heat the water by heating the gold? So the X-ray absorption of the water is very low, but if we hit the gold will get very hot, very, very hot. And that heat will then move into the water and allow us to heat the water. So it was, yeah, it was interesting. And after we took the pressure off, this happened. And if we went in and looked at the sample, what we had made was a kind of gold sponge. And so what we think happened here is the iron was heated up to, you know, 10,000 plus Kelvin. It heated up the water, which melted, and the liquid gold and the liquid supraionic water mixed and created this gold water sponge mixed together. And when you took the pressure off, the different compressibilities meant that the sponge was kind of pushed apart from within as the ice expanded faster than the gold, and then eventually as the ice turned back into liquid water when the pressure came off completely. But lots of analysis on this showed there was absolutely no evidence of any chemical reactions between the gold and the water, even though the temperature we reached was extremely, extremely high. And this led us to this experiment, which is using the couplers that people like Alex Goncharov and Vitaly have been using for years to heat low Z materials with infrared, or materials that won't couple with infrared light, that you heat a coupler and that heats the sample. Well, we would do the same with X-rays, that we would create a crucible of a high Z or mid Z material. We would heat that with the X-rays. Before the next pulse came in, the heat from that crucible would transfer into the sample in the middle, heat that up, and then the next pulse in would probe that. The example there. So you heat up the gold over the next 222 nanoseconds. The heat goes from the gold to the water. Next pulse probes that state, heats up the gold, and we just cycle round, putting in hundreds of pulses. So for this experiment, we loaded, again, very, very large community proposal. We had 47 diamond anvil cells. For those 3 second-generation experiments, there was a total of 130 diamond anvil cells loaded by people from all around the world and either brought or sent to Hamburg. You know, that's probably the best part of $300,000 worth of diamonds. We put in 300 pulses each time, and now with this Egypt detector, we could actually collect individual diffraction patterns, 300 individual diffraction patterns as caused by each pulse. And we collected 250,000 diffraction images in 48 hours. And I just compare that to the 18 years I worked at the UK synchrotron, where we collected 15,000 images in 18 years. And all of this data is stored online because nobody can take it away with them. It's just too much and can be studied in real time on the DAISY cluster. So here are these 300. So this is a kind of waterfall plot of the pulses coming in. Here's the rhodium coupler. Here's the diffraction pattern from the ice, and here are the number of pulses coming in along here. What's interesting, the first thing you see is that the water is compressed slightly before it begins to heat up and then move back that way again. And then we see this BCC ice peak appear here, and we can determine what the temperature is from the lattice parameters of various things. This supposed superionic BCC phase at this pressure. And again, you see it's complicated by the fact that there's, even though the beam is, that we get complicated heating in the rhodium, which is why we've got a paper on the thermal EOS of rhodium out at the referees at the moment to help us understand all of these. But this coupler method worked. I think there is such heating power in the XFEL beam that more recently for, I think, nitrogen experiments, you just hit the nitrogen itself with the beam. You don't need a coupler. Even though the absorption of the sample is very low, there is still enough that if you hit it with enough high power pulses, you can still heat the material up. And the complication, as I said earlier, is that the heating pulse and the probe pulse are exactly the same shape, and that does lead to complications. So again, shifts to the right initially, and then begins to heat, and then all of a sudden the BCC superionic ice peak appears there. Okay, so I'll leave it there. Conclusions. We are very lucky in Europe that we have these two fantastic facilities, Petra 3 in Hamburg and the ESRF EBS in Grenoble. Once the APS comes back up again, you're going to have a machine which is entirely equivalent to the ESRF EBS, where everyone will be able to do wonderful high pressure science. I think things like the ESRF EBS bring synchrotron extreme conditions research closer to the dynamic compression than the XFEL research. And in fact, Petra 3 have a plan to upgrade to Petra 4, again, making this change in the magnetic lattice. And that will truly be a frightening machine in terms of what you'll be able to do with it. And it will definitely become competitive with what you can do at XFELs. So while at the moment the PT conditions are less extreme at the synchrotrons, I would say the diffraction data is definitely best quality at the synchrotrons. IC2 at HED is, I would say, the best experimental setup for DAC research at an XFEL. There are more proposals in the first 6 months of next year. At the moment, they have 6 months of DAC experiments, 6 months of laser compression experiments. So there's I know of at least 2, maybe 3 DAC experiments scheduled for HED in the first half of 2024. You really can obtain extreme P and particularly T conditions in DACs at XFEL. It is easy to heat your sample up to very, very high temperatures, but understanding what those temperatures are and what you're really seeing when you probe it with an X-ray beam of the same size is non-trivial, and we're still trying to understand that. And XFELs at the moment are in the kind of longer wavelengths than we are used to at synchrotrons, but XFELs will move to 25 keV X-rays. We'll be able to get higher angle data, and I think there's a lot to do in phase behavior of liquids once we can get these X-rays. And if you want to reduce your heating, then 25 keV, more penetrating, less absorbed X-rays are the way to do that. But I think in the future, and maybe I won't see it, but synchrotrons like Petra 4 you should be able to get single, good diffraction data from a single bunch, 100 picosecond bunch of X-rays at energies up to 60 keV. And these very high energies might be where synchrotrons like Petra 4 will win over XFELs. So I think that's it there. Yes, so I just acknowledge all of my co-workers in Edinburgh, my main collaborator, AWE, Simon McLeod, the Beamline staff at both Petra and the ESRF, my funders and the facilities. And just to show you, these are the collaborations of those European XFEL experiments. It really is, anybody who has wanted to take part in these experiments and provide samples and send manpower to Hamburg has been most welcome to do so. Now it's breaking up into smaller experimental teams, but it was wonderful while it was going on at the beginning to get a large number of people around the world all up to speed on what we can do in these fantastic facilities. And with that, I will leave it there, and thank you all for your attention.
Thanks very much, Malcolm, for a wonderful forward-looking talk, both the latest work on the synchrotrons as well as all the new work done at the XFEL. So the talk is open for questions, comments. Just raise your hand, put your comment or question in the chat, or just unmute yourself.
Ras, may I?
Yes, go ahead. Valery, how are you?
Great, thank you. Very interesting talk. Thank you, Malcolm. I have just one question. You showed mapping of deviatoric stress. And as I remember, sync equations are for radial diffraction. And mapping means that you're doing axial diffraction. Is it correct? So how are you doing this?
So we are doing, yes, this is all done with the X-ray beam essentially coming along the cell axis. So you can measure it that way. There's a whole framework of analysis to measure it that way using both peak displacement and peak width. I don't think you're as sensitive to it as the radial geometry coming in through the gasket. But one of the things, you can't do a grid scan coming in through the gasket. And we have been keen that once we have a submicron beam, that we can actually probe these things on micron level rather than having some kind of slice across the sample. But there was a paper, was it from Alabama last year on tantalum, where they measured the deviatoric stress in tantalum, or strength of tantalum, using both radial and axial geometries, and showed the data line up perfectly. You can also get to much higher pressures, of course, with axial geometry.
Yeah.
You're not having to use low Z gaskets.
So it's not related to sync equations. This is based on width of peak, right? This is different method.
What I showed you is peak displacement, but we're also now doing peak width and comparing the results. And again, I think that tantalum paper from Alabama had both peak displacement and peak width in it, and again showed that the assumptions which have been used to equate those models result in getting the same answer.
Okay, thank you. I will write you, and maybe you can send me references. Thank you.
Okay, sure, no problem.
Yeah, so there's a displacement of the D spacings within a given spectrum, a given pattern. And that displacement of D spacings is a function of the uniaxial component, a single uniaxial component that you assume for that particular diffraction measurement. And that will be independent of whether you measure it from the radially. And so one thing I was wondering about is the extent to which you see uniformity in the uniaxial component. So you have a T.
Hi, Larry. Valerie, yeah. Valerie? Yeah.
Okay, yes, so that has been very interesting, and we have
similar.
seen
Malcom,
unphysical
Malcom,
changes on a
just
micron scale.
about to end.
Oh,
Go ahead.
does somebody want to mute?
Yeah,
Is that Larry? Okay. We have seen unphysical changes on micron length scales, from micron to micron, in the value of T using the peak displacement. But that has not, and I have a student working on this right now with data we collected earlier in the year. And so this is why we've also started to look at the peak width method of extracting the same information.
right.
This also came up in a call the other day about, are we conflating peak shifts due to both deviatoric stress and things like stacking faults? And so people were doing some analysis on an experiment we did using dipole back in May, and they're assuming their peak displacement is coming from stacking faults. And the question they were asked were, well, how do you know there's not some kind of uniaxial pressure component to that as well?
Okay, Daniel, go ahead.
Hi. Question about the evolution of phase boundaries for across the lanthanide series. I think it's one of your first slides.
Yeah.
I was curious. I was a little surprised that although there is a lanthanide contraction as you go from lanthanum to lutetium, and therefore the volume per ion becomes smaller, your first phase boundaries are shifting to higher pressures as you go to lighter rare earths. Can you comment on this, whether the lanthanide contraction plays any role? It seems that it does the opposite. Something else is going on.
Okay, I wish I could, and also because I was in an email exchange with our computational colleagues this morning about this. I would have to go and read up the classic papers from the 80s on, was it Johansson, as to try and explain, why, for example, in this DHCP phase, why, as I go across the period, does it appear at higher pressures. So you can see your new phases come in. So for the lower Z members, you don't see HP2, HR4. It's only at the higher end of the sequence you see these phases come in. So there is an explanation, but I can't remember what it is at the moment. But there are a series of classic papers on trying to explain this. You'll come up with a common phase diagram for both the lanthanides and the actinides. In terms of the behavior of the electrons and things like that, but I can't remember the details right now. But if you drop me an email, I'll send you a couple of papers. The
Sounds
kind of
great.
classic big papers on this.
Sounds great. Thank you. No problem.
Thank you.
But what is interesting, it means you can probe the very high pressure behavior of thulium and lutetium at very low pressures in things like cerium and lanthanum, for example. And personally, despite all the attraction and interest that lutetium is getting at the moment, we don't feel the need to break any diamonds, just showing that this thing is, it's going to need 300-400 GPa in order to make it behave like these lower Z members at much lower pressures. But there's no reason to expect why lutetium, for example, won't follow the same structural sequence as all the others, just at very much higher pressures.
More questions, comments? You mentioned the 9-fold compression of potassium at 200 to 250 GPa.
Rubidium, yep.
Yeah, and as you know, hydrogen at those pressures is about 12 to 13-fold compressed.
Yes, we hoped it was going to be higher than hydrogen, but it's not.
Right, and it's far from the the Thomas Fermi limit. In fact, it's still molecular and not even a metal, those conditions. So
Yeah.
interesting.
So I mean, we've got very into this, looking at the equation of state now and using these deviation from linearity to see changes in behavior. And as I explained to my undergraduate classes, the eye is very, very good at seeing linearity and departures from linearity. And it's remarkable, even if we feed other people's data into these equations and linearize them, that quite small, subtle changes in compressibility or small, very small discontinuities, produce remarkably amplified effects in these linear plots. And what if we done something recently on iridium? It's just been accepted. We just sent the proofs back yesterday. And if you overlay all the compression curves of iridium in a standard PV plot, they all look remarkably similar. But when you linearize them, they are remarkably different.
Yes, very
and
nice.
very sensitive to the value of V naught, for example.
Mhm.
But it would be nice. I've never compressed anything up to 10-fold compression. We hoped rubidium would get there, but the diamonds failed. The diamonds failed first, unfortunately.
Let me ask you the question I asked you at the March meeting, and that is, do you have any more information on possible disequilibrium in your FEL experiments when you heat to something like 10,000 Kelvin, disequilibrium between the electronic temperature and the ionic temperature? Because that goes to the whole mechanism of how you couple.
Absolutely, absolutely. So that paper that Matthew wrote using lamps was our attempt to get into and understand the physics of this. There is a fascinating area of physics there. The first nanosecond would be fantastic, but in order to do that, we need to split an X-ray pulse into two pulses separated by a nanosecond. And at the moment, we can only send in two separate pulses, 220 nanoseconds apart. So all of that physics has happened by then. But I think what would be great for the future is, particularly in a diamond anvil cell, where the sample can't go anywhere. It can't vaporize and just blow into space, that there will be release waves as the pressure. There's the whole physics of heating up the electrons, and then the coupling between the electrons and the ions, which happens over kind of 10 picoseconds or so. And then there is the physics of, what does your sample do when it suddenly finds itself at 10,000 Kelvin and a megabar, and it can't go anywhere because it's clamped in a diamond anvil cell. What would happen if we just put a piece of tantalum foil is that the material would just vaporize and blow out front and back. But it can't do that in a DAC. So to be able to probe what the release waves are doing as they travel through the sample, travel through the PTM, reflect, interact with the diamonds, would be fascinating. But we just don't have the control over the X-ray pulses to do it yet. You would really need to split your pulse and be able to bring it in, with splittings, hundreds of picoseconds over a range of 10 nanoseconds or something.
Right.
But completely unprobed at the moment. Lots of people have done this in foils at ambient, but not in a sample clamped in a half a megabar in a diamond anvil cell.
Thanks. Any more questions, comments?
Just wanted to make a comment on with Dan Haskell's question. Not sure I understood what he was after, but maybe it has to do with the work of Pettifor. There's a beautiful Fisrev letter from Pettifor that argued that the heavy lanthanides have fewer d electrons than the light ones do. So lanthanum has a lot of d electrons, and that's why it's superconducting. And the heavy lanthanides have far fewer d electrons, and of course that's important for the structure, and you can explain the structural sequences like that. And so that must have to do with Dan's question, I think, to explain it. The fact that
Excellent.
the core gets small very, very quickly, more so than the outer electrons when you go to the heavier lanthanides. So the electrons are not being squeezed very much, the conduction electrons. So it's not much D character. You get more D character when you compress the conduction electrons. So lanthanum does the best job and lutetium does the worst job.
Thanks, Jim. So I've no idea who's on this call because once I start sharing my screen, I can't see anything. So yes, you're quite right. It's the Pettifor paper I was thinking of, not a Johansson paper. But you're right, that is a classic on all of this.
Thanks, Jim. More questions, comments? If not, join me in thanking Malcolm for this wonderful after dinner speech.
Thank you. Thank you for not giving up on me.
Okay.
We think it's taken 2 years to arrange this. So excellent. Thank
Okay.
you.
A
Good
happy
to see
holiday.
everybody.
Yes.
Yes, happy holidays, everybody.
Happy
Bye.
holidays. Bye now.
Bye.
Thanks, Malcolm. Great talk.
Thanks, Tim. Good to see you.